This is the fifth video on the National 5 topic of circle geometry, and in this video we'll be applying trigonometry to the shapes we've looked at in previous lessons. The right angles in the triangles and kites formed by properties of circles allow us to work with our trigonometry ratios to find sides and angles. The three trig ratios, sine of an angle is the opposite side divided by the hypotenuse. The cosine of an angle is the adjacent divided by the hypotenuse. The tangent of an angle is equal to the opposite over adjacent. These three ratios are given to you at National 4 level. At National 5 we need to remember these ourselves. These wee triangles are a nice little memory aid. The word SOHCAHTOA, a little mnemonic which just reminds you of the order to write the letters down in. We can apply these ratios to similar sort of examples we saw in the last lesson. So I'm going to find the stated lengths and angles for these triangles here. So I've been given the information AC equals 14. So I see this chord here is 14, and I've been told OC is 16. And I've been asked to find the angle BCO. The angle BCO, if I trace out those three letters from B to C to O, would be that angle there. The dashes show me I've got a bisector, so I know they're running perpendicular. They've formed a right angle. So this allows me to put a right angle triangle together using C, O, and B. The hypotenuse of this triangle, well, that's just the radius. So I've used the 16 meters. BC, that's half of this line AC here. So I've half 14 to get 7. And I'm trying to find this angle in here, which I'm going to label X. When using trigonometry, I need to label my sides. So OB, this side would be my opposite. This would be my hypotenuse. And the side next to my angle would be the adjacent. I'm trying to find the angle, and I know the adjacent and the hypotenuse. So, looking at my rules, the one that lets me use the adjacent and hypotenuse is cosine ratio. I'm trying to find the angle, so covering that up shows I need to use adjacent over hypotenuse. So I know the cosine of x is the adjacent 7 over 16. Now, I don't want the cosine of x, I want the value of x, the value of the angle. So to do that, I need to find the inverse cosine. Remember, typing this into our calculator, cosine button, I've got the inverse cosine above. So I can push shift, cosine, brings up this cos minus 1, the inverse cosine, and I can just type 7 over 16 and close my brackets. It's also worth remembering, if you've got a calculator that doesn't have the fraction button, typing in as a division will also work. So I'll just write down a little statement. The angle BCO is 64.1 degrees. Second example, working with a semicircle this time. I've been told that QS is 12 millimeters. I've been given the angle QRS, so QRS, I've been told that angle there is 43 degrees, and I've been asked to find QR. So, again, two chords inside a semicircle. That's going to form a right angled triangle. So, I've taken a triangle, I've rotated it just to make it a bit easier to work with, but notice I've got S at my right angle, Q there. I've been told QS, this side here, is 12, so I've put that in there. I've been told QRS, so that's the angle R, that's 43 degrees. I've been asked to find QR. I've been asked to find QR. So if I label QR straight away, I can see that's the hypotenuse. This 12 millimeters is opposite my angle. Now, I've got the adjacent here. I'm not going to label it because I'm not working with it. So I'm looking for a rule that uses opposite and hypotenuse. So that would be me using the sine ratio. I'm trying to find the hypotenuse. So that means I have to do the opposite over the sine of my angle. So I know the hypotenuse is going to be the opposite 12 over the sine of my angle. So I can type that into my calculator. 12 divided by sine 43, or you can type it in as a fraction. Remember to close your brackets. And write down your unrounded answer. The hypotenuse, QR. Just write down my rounded answer and round it to one decimal place with my units. Final example. Well, we've looked at a perpendicular bisector. We've looked at a semicircle here. So now we'll look at a tangent. Okay, so straight away I've got a tangent. So strictly speaking, I should have in my statement here mention that this is a tangent, but I've left that out. I've got my right angle there. I've been told OY is 20. I've been told the angle XOY, so XOY, I've been told that angle is 75. And then, well, I've been asked to do something a bit different. I've been asked to find YZ. Well, first things first, I want to draw my triangle out. So my right angle, my 75 degrees, my 20 centimeters I'll put in. I know how long OY is, and I want to find this distance here. This is a case of being a bit sneaky and realizing, well, this distance is the same as this distance. The lines OZ and OX are both radiuses, or radii. So if I find the radius here, I can subtract it from the side OY and be left with YZ. So I'm here trying to find OX. I'm trying to find the adjacent. I've got the hypotenuse. And looking at my rules, the one that works with adjacent and hypotenuse, I'm using the cosine ratio again. I'm trying to find the adjacent. So here I see I have to do cosine of my angle times the hypotenuse. So the adjacent is cosine of 75 times 20. I can type this into my calculator and get my unrounded answer. So I know OX, the radius of this, is going to be 5.2. I know the line YZ is going to be the whole of this side, take away the diameter. So, using my numbers, I've got the whole of this side's 20, the diameter, the radius, sorry, is 5.2. Subtracting them tells me that YZ is going to be 14.8 centimeters. Over the page here, I've got a new sort of challenge question. I think we may have looked at this one when we were dealing with similarity, but try and have a go at this one yourself with a fresh pair of eyes and realizing, uh, being able to realize where the right angles are yourself.